Okay, today's unit is the third section of the first unit. In our current textbook, that is chapter 6, and it'll be section 6.3. What we're doing is looking at base systems. So like base 5, base 8, base 2, what do those mean? So first of all, let's just talk about our number system, which is base 10. We basically live in a base 10 world. We use 10 digits, 0 through 9, and every placeholder will be 0 through 9, and our place values, as you can see, are 1, 10, 100, 1,000, going the other way, it's 0.1, 0.001, etc. So you're used to thinking that way in base 10. So what is a different base system? Well, for example, base 2, we basically keep the Hindu-Arabic digits, but we're only using the zeros and ones. If we're in base 5, we're using 0, 1, 2, 3, 4. Notice we don't use the 5. And then base 8 is 0, 1, 2, 3, 4, 5, 6, 7. And we don't use the 8. So that's a little background. You can read through those first couple of slides. They kind of go into more detail about place value and all that stuff. My main thing I want to accomplish with this video is just basically how to convert from binary to base 10 and then base 10 to binary. But I at least wanted to mention, okay, what is a different base system? So, for example, again, base 2, what we're going to start with for right now is we're only, in our world now, we're just zeros and ones. You could actually think of it that way. You know, the old world, before you learn this section, everything was base 10 and your digits were 0 through 9. So now in binary world that we're going to work with on this video will be everything zeros and ones. So, one thing I do want to mention, you know, what does a base number look like? Well, binary number might look like 10101, and then you put the subscript to indicate it's base 2. Again, notice all my digits are zeros and ones. This would be what a base 5 number looks like. And again, all the digits are less than 5, 1, 3, 4. So you couldn't have 1, 3, 6, 2 base 5. That wouldn't be possible. If you're in base 5, again, you have to have digits 0 for 4 only. So let's look at an example. What we're going to take is the binary number 1111, base 2, to base 10. So what am I going to do is, again, here we're converting from base 2 to base 10. What I'm going to do is write down the digits. So all my digits were, I had 4 ones. And each contains a place value. So we aren't in base 10, so everything is base 2, and we would start at the 0 power. Think about 10 to the 0 power is 1. 10 to the 0 power is 1, so it's the ones place. 10 to the first would be 10, so that represents the tens place, which would look like 2 to the first here. Remember, we're in binary. And then plus 2 squared, and you just take the power up as you go across. And that gives us 1 times 2 cubed, 1 times 2 squared, 1 times 2 to the first, 1 times 2 to the 0. So, just, you know, get your calculator. This is computation from here. 2 cubed is 2 times 2 times 2 is 8. 2 squared is 4. 2 to the first is 2. And then, of course, anything to the 0 power is 1. So this will be 8 plus 4 plus 2 plus 1. And that comes out to 15. We'll do one more going from binary to base 10. This is example 3 from the PowerPoint for this section. So notice my number is binary. It's 101010. And we're going to base 10. So we're going to write down the digits. And again, that's 0 times 2 to the 0. And you just work your way up. 1 times 2 to the first. 0 times 2 squared. 1 times 2 cubed. 0 times 2 to the fourth. and then 1 times 2 to the 5th. So now we'll do the computation part, which will be 1 times 32. 0 times 16 is just 16, if that's okay. It's going to come out to 0, 8, and then of course this will be 0, and this will be 2 to the first, and then this will be 0. So if we add 32, 8 is 42. And that is an example of going from binary to base 10. So what we'll do next is we'll go from binary to actually base 10 to binary. So I'm going to do one that's not in the PowerPoint, okay? So this is not in your current notes. It's almost an extra example. And then I will do one from the PowerPoint. Okay, so what I'm going to do is, one thing about the PowerPoints, they're kind of large. So I'm going to do a really small one to kind of start. So I'm going to take 20 in base 10 to binary. All right? And we can just say a binary number. Actually, let me write that a little bit neater. That was really messy, my bad. So we'll take 20 to a binary number. So what we're going to do is we're going to work backwards. So think about what we did. Converting from base 2 to base 10, we basically just wrote out as a strand of powers of 2, adding up each term. So we're going to reverse the process. We're going to take the 20 to a string of powers of 2 that are added up. The problem is, how do you do that? Well, you've got to work backwards, which the opposite process of multiplication is division. So what we're going to do is what's called the division algorithm. And what you do is I'm just going to write down the powers of 2 to start, and then we're going to divide out the actual number. But let's get this written down. So 2 to the 0 is, of course, 1. 2 to the first is always just the number back. 2 squared is 2 times 2 is 4. 2 cubed is 2 times 2 times 2 is 8. And we just keep going. 2 times 2, multiply of 16. So, what you do is when you exceed the number that you're starting with, which is 20, you're going to have to stop. So we're going to actually start at 16 and divide out. So we're going to divide 16 into 20, which will go in one time. And my remainder is 4. So what we did was we took the highest power 2 that we could divide into 20, which was 16, which is 2 to the 4th. Took it into 20, it goes one time, 4 left over. And you're just going to keep taking the dividend, or your remainder, and dividing into it. So now what we do is we got to find, divide into 4. So we go up a step. Well, notice 8 doesn't divide 4. It's too big. So we actually have to skip it. I'm going to write skip there. And we're going to go up to 4, which, if we take 4, goes into 4 once, and my remainder 0. Now, if you hit a remainder 0, you're done with the division part, which we are. So the only dividing factors we have are 2 to the 4th and 2 squared. So I'm going to write down 20 as 1, because it went in once, times 2 to the 4th, plus, we skipped 2 cubed, so I'm going to put a 0 as a placeholder, plus 1 times 2 squared. And then we still have to worry about, because this did work, we essentially had to skip 1 and 2. And I'll get back to that in just a second, okay? Let me write that out. So we're going to have 2 more zeros. So we actually had 3 zeros that served as placeholders. Because remember, in our strain of powers, you have to have everything represented. 0, 1, 2, 3. So we have to have each power 2 represented up to the highest one that divides out, which is 2 to the 4th. So at this point, we just go backwards. So just pull out the leading coefficients, because, you know, if you're going backwards, it'll just be 1, 0, 1, 0, 0. That is actually my binary number. And I'm done. Now, going back to what I was talking about, this idea, okay, you're saying, well, why did I put those 2 zeros there? It's kind of the same idea as, you know, remember when you're in grade school, you kind of been doing all this all your life. It's like if you actually took 2 into 200, and this is just an illustration. The numbers here have nothing to do with this problem. It's just an illustration. But 2 essentially goes in 100 times, because 2 goes into 2 once, and what do we have to do? We don't say the answer is 1. We say, hey, we need something for the tens place, something for the ones place, because there's the decimal point. So basically, these zeros, when you're dividing out and you divide out early, which that's what happened here, you have to still work with this idea of zeros as placeholders. And that may not happen in all the examples you do. It may be that you use every power going up. That can happen. But sometimes you have to skip and put zeros as placeholders. Okay. One last example, and this doesn't match the PowerPoint, but in some ways that's nice, because if you want extra examples to work, you can do, and then of course the solution is provided for you, so you can work and check. So we'll just kind of handle it that way, but at least you got to see 2 examples worked out in detail by hand, and then you can work from there and do the practice. All right, so let's do 50 to a binary number. So I'll put down my powers of 2 again, and these will be the same. So let's see, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. And I think the next one will be 64, so we'll have to stop. Actually, I think I will put these papers back under it. It seems to help. I'm having trouble writing. All right. Okay, so we're going to start at 32. 32 divides into 50. Again, 64 is too big. That goes in once, and we have 18 left over. Carry over your 18, and look and say 16 will actually divide that. Once, 2 left over. Now we do have to skip here. 8 and 4 are too big. They don't divide 2, but 2 will divide 2 once, and we get a remainder of 0, so we're done. So this is 2 to the 5th, 2 to the 4th, and 2 to the 1st. We actually use 2 to the 5th, 2 to the 1st, and 2 to the 4th, and 2 to the 1st. So we will have 1 times 2 to the 5th power. That went in once here, so 1 times 2 to the 4th. Again, we went in once. With binary, it either is going to be 1 through 0, by the way, obviously, because those are your only digits. We do have to put 2 zeros as placeholders. And 1 times 2 to the 1st, and then 0 times 2 to the 0. So my final answer is 1, 1, 0, 0, 1, 0. Pulling out, extracting out those coefficients that create your binary number. So please email me if you have questions. I wanted to do 2 conversions of base 2 to base 10 and 2 of base 10 to base 2. I'll have a separate video that does the, say like a base 5 to base 10. So, anyway, that's at least a hand, that is doing the technique, division algorithm technique. Now there is what is called the tabular method, which is taught in the book. I thought about maybe actually doing it that way. The thing is, though, it kind of cuts out the step with the division. I thought actually that might, you're kind of doing that in your head, so in some ways, even though you're writing it kind of awkward, in a lot of ways it's simpler because you see everything written down, because you divide and then get the remainder, divide, get your remainder, and when you do the tabular, you work straight down and you actually only show the remainders you're going down, so it's a little confusing. But feel free to, because on the test, obviously, you can do these by tabular or by division algorithm. Okay, that concludes this one. The next video will be on how to convert basically non-base 2, non-base 10 to base 10 and so forth, then base 10 back to some other base like base 5 or base 7.